Also, just going to pause this. Now we're going to start. Okay, so this unit's kind of all about graphing polynomials. So we will need some information from advanced functions. And then we're going to kind of build on that and see how derivatives can help us get a bigger picture of exactly what some of these polynomials look like and how we can use them in functions to see some more information about them. So in grade 12, advanced functions, a lot of you guys asked when we were sketching polynomials, how do we know how high some of these mountains and valleys or how low some of these valleys go, right? Like how do we know if the function's like this or how do we know if it's like a big swoop, right? Well, that's where calculus comes in because calculus actually helps us find the locations of these turning points. And without that, we would have to just kind of like guess and check and get some estimates. Firstly, I just want to kind of do a couple labels so that we know what these words mean. So some of these you would have seen in advanced functions. Local min and local max. These are going to be anywhere that you have a mountain or a valley. Okay, they don't have to be like the max or the min, but our local mins are going to happen at the bottoms of valleys and our local maxes will happen at the tops of mountains. So we've got a couple local min here. Okay, these two would be local min. And we've got a local max right here. And when we say local min and local max, we're usually talking about the x-coordinate of that point. So where is the local max? Well, here the x-coordinate is 2, so we would say there's a local max at 2. There's 2 local min, one's at 4 and one's at, I don't know, not quite -2, somewhere between -2 and -1. So here we're talking about the x-coordinate. Now, when we say local min value and local max value, we're still talking about the same point, but this time we're talking about the actual y value of that point. So these guys, we're talking about the y coordinate. So how high or how low does that point go on the y-axis? Or not on the y-axis, but as far as the y-coordinate. Okay, so here we've got a local max value at 0. We also have local min values maybe around like -1 and -4. Okay, when we say the word local extrema or turning points, we're talking about any local max and local min. So all of the local max and local min points. Okay, so if a question asks you find the local extrema, we're talking about any possible local maxes, any possible local mins. Okay, and then absolute max, absolute min, it is exactly as it sounds. So the very top point and the very bottom point, be aware that a graph could have neither. It could have one of the two. For instance, if it's an odd degree polynomial, we know that thing continues forever in both directions, right? Because it has opposite end behavior. So that would actually have no absolute max or min. Whereas something like this, an even degree polynomial, has, this one is actually an absolute min right here, because that's the very lowest point of our graph. So these will be the very highest or the very lowest point, depending on whether it's max or min. Okay? Okay, so this guy, this local min is also an absolute min, but we would still call it a local min. And this guy doesn't have an absolute max because it goes up forever. Zainab? Okay. So in order for something to be considered a local min or a local max, the function needs to change from increasing to decreasing or decreasing to increasing. Okay? If that doesn't happen, it's not a local min or max, right? So the function must change from increasing to decreasing or decreasing to increasing, just like we talked about in advanced functions. That's the definition of a turning point, right? So in order for these things to happen, it must change from increasing to decreasing or vice versa. Okay, so we must literally have like a valley that's happening or a mountain that is happening. Pretend that's curved. Looks more like a mountain though. There we go. So far so good? Yes? Min-min, obviously. Yeah, min-max, thanks. Good? Okay. So critical number. So when we talk about critical numbers of a function, we're essentially kind of like talking about the local extrema. So it could be anywhere where we have a local min or max, or also anywhere where the function is undefined. Okay? So I'll just give you kind of like the definition. So we'll have is a value in the domain. We'll say it's A. And what's going to happen is the first derivative, if it is a critical number, will actually give you 0. So that's kind of how we know that we have a local min or max. But there's also some other information that we need to take a look at as well. Or what might happen is your first derivative at that particular value will not exist. For instance, if it's an undefined point of the function, our derivative won't exist for that point, like an asymptote. Zainab? No, A is just any number. We're just saying it's a variable. Okay, so critical numbers will be kind of similar to turning points, right? Because we know at turning points, or some of us know, the derivative is 0, right? Okay, this one also adds in the area where the function might be undefined for that particular derivative. Okay, I think we kind of already know this, but it's good to know the idea of like increasing and decreasing. So can somebody tell me how we know a function is increasing? What would we be looking for? Mark? Yeah.
Moving away from 0 is not increasing. Decreasing if it's like approaching 0 or
Okay, so a really easy test, you can just slide your pencil along the function from left to right. If your pencil's going up, it's increasing. If your pencil's going down, it's decreasing, okay? So slide your pencil left to right, or a pen. Okay, if your pencil goes up, it is increasing. If your pencil goes down, it is decreasing. Okay, Okay? When we say increasing and decreasing, we're talking about how the y values of the function are changing, right? So we're saying as I kind of move my pencil along, if my pencil's going up, the y values are increasing, right? They're getting bigger. But if my pencil's going down, the y values are getting smaller. Okay, they're going towards 0 or maybe even getting more and more negative. So that would be decreasing. Okay, so when we check, yeah, sorry, Mark.
So like if you have like a polynomial, it's like one big parabola.
Yeah.
And it's like a max.
Yeah, so it's a parabola facing down.
And it's in like the like under the x-axis.
Yep.
Is it still
Yep. So it will still have half of it that's increasing. The first half will be increasing, and the second half will be decreasing, regardless of where it's positioned on the graph. Now, if it's completely under the x-axis, that whole function is in the negative section of the graph, right? But there's still increasing sections and decreasing sections. Good question. Okay, so this is a little test that we're going to do to find turning points, right? We're going to find the derivative and see where it's equal to 0. That will give us locations of turning points, but how do we know whether those are maximums, minimums, etc., right? Zainab?
I'm kind of confused about like critical number. Like, is it just we find the derivative of the function, I guess, equal to 0? Like, I don't understand.
Yeah, so you guys did some of these questions in the first chapter. So you're going to find the derivative, you set it equal to 0, and you solve for the x's that make that possible. Yeah, yeah. Okay, so we're going to find where it's equal to 0. Or we might even be able to, like if I just asked you, is 3 a critical number of f at x, you could find the derivative and sub in 3 and see if it equals 0. If not, then it's not a critical number, right? So it depends on the question I ask, but most of the time you will be finding the critical number by setting the derivative equal to 0 and solving. Okay? Okay, so how do we know whether it's a local min or local max or maybe even neither? Well, we have to look at what is happening around the function. Okay, so in order for something to be a local minimum, when I find f prime at x, I know that at this point, wherever that local min is, we'll have f prime at a equals, or maybe I should say a, whatever, it doesn't matter. We'll have the derivative equal to 0. If it's a local min, though, I'm going to see that my function here goes from negative to positive, the derivative, right? Because that tells me that the original function was decreasing, has negative tangents, and then it has positive tangents, right? So I'd be looking to see if my derivative goes from negative to positive. That would tell me that I have a local min. Okay? If I have a local max, I will check to see if my derivative changes from a positive slope of a tangent to a negative slope of a tangent, right? So I'd be looking for a change from positive to negative to see if I have a local min. Now, if I have neither, I'll see that there is not a change between negative to positive or positive to negative. So maybe it's like positive, positive, or negative, negative. That tells me that I have neither, okay? And a case like that might be where I have kind of like a curve where, of course, I have a horizontal tangent right here, but this is like positive to positive. So I'm not going to see a change between positive and negative. So you must see a change between positive and negative for that thing to be considered local min or local max. Okay? So this one you'll see no change. Either positive, positive, or negative, negative. Mark.
So if you had like a curve but it flattened out like that,
Yep.
would it be still neither?
Yep.
Like even if it went negative to positive?
I mean, that is basically this, right? Like if this were kind of like going like that, it's still changing from increasing to decreasing, right? So we're just looking to see, like, are the slopes of the tangents changing from positive slopes to negative slopes or negative slopes to positive slopes, right? If not, then you would say neither. Okay? Any other questions? Okay, So what we're going to do is kind of set up like a little sign chart, kind of like what we did in advanced functions, just to see like what's going on with the function. So we will set up something similar, but this time we kind of want to test in our derivative so we can kind of see what's going on. And all I'm really concerned about is whether that second derivative is positive or negative after I've found those critical numbers, right? So I'm going to find my critical numbers. I'll do like, for instance, negative infinity, and then I'll put my critical number on the top of these lines. Again, kind of like we did in advanced functions. And if you want to put a line there for negative infinity, you can do that as well. And then I'm going to check out kind of like what's going on with my derivative there. So I will have to find the derivative. And then I'm going to choose some test values that fall in these intervals to put into my second derivative. Right? So I want to see what's happening around these critical numbers so I can decide whether I have local min, local max, or neither. So what I would do is test in my first derivative. Okay? Now let's just say, just for our purposes now, let's just say you plugged in a test value and you got positive, and then you plugged in another test value and you got negative, and then maybe you plugged in the last one and you got another negative, okay? Just for our sake. And then usually what I do is I get a bit of an idea of what is happening for the function f at x. So from these, I can tell this. I can tell that my function is increasing. I don't need to make it curved or anything like that. We're not drawing the function just yet. So I'm just going to show this for increasing, right? So I know that we have positive slopes of my tangents. And then I have a critical number somewhere around here. And then I've got some negative tangents. So I've got some tangents going in the negative direction. And then I've got another critical number here. And then I keep going negative. Okay, so what has this just told me? So what is this point right here? You can kind of see that this is making a mountain. So what can I gather about this critical number? Local max, right? Yeah. Okay, so now I know this is a local max. What can we gather about the second critical number over here? It's neither, yeah. So if there's no change from negative to positive or positive to negative, this guy's going to be neither. So likely what's happening here is we have kind of like a curve that goes like this, and then it continues downward. Okay?
What did you say CM stands for?
Critical number. Yep.
Like does like for like the two negatives?
Yeah.
Could it also just like go straight?
No, because in order for us to have a critical number, the second derivative has to be 0, meaning, or sorry, I keep on saying second derivative, first derivative, meaning that I have to have a point where my slope of my tangent is 0. So it has to kind of go in that little S shape. Okay? Okay, so your local extrema are going to occur where the first derivative changes signs. Okay, so positive to negative or negative to positive. Okay? And then, of course, like we said, if the sign of the derivative does not change, like it goes negative, negative, or positive, positive, you do not have local extrema there. We can still be considered a critical number, but it's not local min or local max. Aiden?
How do you find the critical numbers for the sign chart if you don't have the graph in front of you? You have to like.
So you have to solve algebraically. So you have to find your derivative, set equal to 0, and solve for where that's true. Okay? So if the sign does not change, you don't have, it's not, that critical number is not considered a local extrema. If the sign, okay? Yeah. So when I'm looking at this chart, and I do my test values, I'm seeing that the signs are changing between the first critical number here. It goes positive to negative, but between these two guys, it stays negative, right? So I would need it to change from positive to negative or negative to positive in order for that critical number to be considered as like a local max or a local min. You're getting too far. Don't worry, we'll do some examples, okay? I'm just kind of showing you guys the setup for right now and giving you some foundational knowledge. We're going to do it algebraically, though. Okay? Yeah.
So you said like a critical number would be like f prime of x equals dne.
Yeah.
So like
So that happens on like asymptotes, right? Or on like the cusp of a point,
okay.
maybe. Like if I have like endpoints, my derivative can't exist there, but it still might be a local max or local min point.
So it can still be a local max if there's nothing there.
No. I'm just saying, like, if I have a function where I have, like, let's say I have, like, endpoints or something like that, I still need to look at these endpoints because they might be absolute maxes or absolute mins. So they would still be critical numbers, right? Even though my derivative at that particular point, like we kind of talked about, if I have a cusp like that, my derivative does not exist, right? This is an absolute max right there, right? So that is an important point. Yeah. Go ahead. Okay, let's move forward. All right, so we're just going to do some labeling, and then we'll get into a couple examples here. So firstly, let's talk about f at x. The function f at x is positive in the sections above the x-axis. So here and here, we would say f at x is positive or greater than 0, right? That's where our function is positive. And our function is negative, of course, underneath the axis here. So our regular function f at x is negative here and here. So we would say f at x is less than 0. Okay. Actually, I just want to move this over. I feel like that's not going to work. Never mind. Okay. I also have sections where my first derivative will be positive, right? The sections where my first derivative will be positive are the sections that have positive slopes of tangents, right? Or in other words, on the increasing sections of f at x. So what color do I want to use here? We'll use pink. Okay, so this section here, up until this point, and this section up until this point, that is where my first derivative is going to be positive and where my function f at x is increasing, right? So f prime at x in this section will be positive, and also in this section will be positive. Okay, and then in the in-between section here, this section is where my f prime at x is going to be negative. Okay, that is where f at x is decreasing, right? Okay, and then we've got a couple other important points here. Some of the important points are the zeros, which are, of course, where f at x equals 0. Okay, on both of those points. And then our last important points are where f prime at x equals 0. Let's see what I want to use for that. Orange. Okay, and that is here. So we know that this is a critical number, right? F prime at x equals 0, and then also this guy right here, right? F prime at x will equal 0 there. Zainab. So we're just going to talk about first derivative for right now.
And that's just like the first.
The first time you take the derivative. So the initial derivative that you get from the function. Okay, if I take the derivative of the derivative, that's the second derivative, right? That's kind of like how we were talking about the position function. Then if I take the first derivative of that, I get the velocity function. And if we take the derivative again, we get acceleration. That's the second derivative. Good? Okay, so where f at x is increasing, f prime at x will be positive. Does that make sense? Because the tangents will be positive on the increasing sections of the graph. And then obviously vice versa for the other way around. Any questions? Okay, let's move on. Okay. I'm just going to name these points to start. And these are going to be kind of the important points. The endpoints are always important points of a graph, okay? Because they might be absolute maxes or mins. So I've got a couple important points here. Remember what we talked about with you focusing and being quiet? This is the time. Okay, so we're just going to label these guys A, B, C, D, and E. Again, I'm labeling the endpoints because although the endpoints are not local mins or local maxes, they might be absolute mins or absolute maxes. So local mins. What points are local mins here? Not values. I just want the points. We just labeled them. Oh, yeah. Okay, so where are the valleys? Okay. Okay, just C. Okay, must change from increasing or decreasing to increasing to be a local min. How about local maxes? B and D. How about absolute min? A, yeah. Okay, that's why we need the endpoints. Absolute max is D, yeah. Yep. Good. Okay, so endpoints are always important if we have a function that doesn't continue forever. Just remember that. Yep. You will have to know, like, it will have to give you like a domain of where the function starts and finishes, and then we'll just like test them in the original function to see how high or low they go. We'll talk about it, don't worry. You guys are, I like that you guys are asking questions, but you're getting so far ahead. Okay, so this may answer some of your questions. So we want some important points here that are called critical numbers. I find these by finding the derivative, setting it equal to 0, and solving, okay? So let's just start by finding the derivative. Okay, 6x squared minus 18x minus 24. Okay, now I want to know where the derivative is equal to 0. Okay, that is where I have a turning point, or potentially a critical number. Yes, so I want to find where the slope of the tangent equals 0 on the original function. Okay, so I think we can make our life a little bit easier here by common factoring. And then I just want to factor this guy inside the brackets. That should be pretty quick. I think we get x minus 4, x plus 1. So my x equals 4 and my x equals negative 1. So we would consider both of these to be critical numbers, right? So anywhere where the first derivative equals 0, What am I doing? Okay. Now, if I want critical points, I can find a point by plugging these x values into my original function and finding their y coordinate. If I'm just looking for critical numbers, those are going to be the x values, right? Critical point, x, y coordinate. Okay? So I'm also tasked here with stating where the function is increasing or decreasing. So I'm going to have to just create a bit of a sign chart like I showed you above to figure out where the first derivative changes from negative to positive and positive to negative. Okay, so we're going to make a little chart. We're going to arrange the critical numbers, lowest to highest, starting at negative infinity, and then we'll go negative 1, and then 4, and then infinity. Okay, I want to find out what's going on with f prime at x, and then I'm going to write just a bit of a picture of what would be happening with f at x in that section. Okay, so what I need in order to do this are just some test values that fall within these intervals. Okay, we should be pretty used to making charts like this. So here, maybe I'll choose negative 3, and then we can choose 0. That's always a good one to choose if you can. And then here, maybe we choose 6. These are going to be my test values. They should not appear anywhere in my final answer for where this function is increasing or decreasing. Okay, they're only test values. Okay, so here's what we're going to do. We're going to take a couple seconds and just sub these into our derivative and record whether we get positive or negative. Okay, so if I sub in negative 3 here, for instance, I get a negative times a negative, which gives me positive in that section. Okay, if I sub in 0, I get negative times positive, which gives me a negative in that section. And then if I sub in 6 here, I get positive times positive, which gives me positive in this section. So I'm literally just taking these values and I'm subbing them into these x's and recording positive or negative. Thank you, Vanessa. Okay, so what does that tell me about f at x? It tells me that it's increasing, and then I have a critical number here, and then it's decreasing, and then I have a critical number, and then it's increasing again. Okay, so I already know now that I have a local max at negative 1. I have a local min at 4. This question doesn't ask me about that. It just asks me where the function is increasing and where it's decreasing. So the function is increasing where the first derivative is positive. It's decreasing where the first derivative is negative. So increasing intervals. Again, I'm not using the test values. I'm actually using these values up here. Okay? So it's increasing from negative infinity to negative 1. Do I include negative 1 in my set? No, because the derivative is actually 0 there. So it's neither increasing nor decreasing at that point. It's derivative of 0. Okay, and then we also have a second interval where it is increasing, which is from 4 to infinity. Okay, and then decreasing on the opposite interval, right, from negative 1 to 4. Okay, I'm using interval notation here. Can someone explain to us why we don't use square brackets for negative 1 and positive 4? Mary. Right. The derivative at those points is equal to 0, so it's neither increasing nor decreasing at those critical numbers. Okay, good. All right. If I happen to have the graph of this function, we could actually do a really quick sketch. We don't necessarily have to create this sign chart, right? Like if this is an easy guy to sketch, I think we can see where the first derivative is positive or negative. So if I actually just sketch this guy out really quickly, the graph of the derivative, what do we know about the graph of the derivative? Well, we know that it has x-intercepts at 4 and negative 1, right? So if I'm just doing a really quick sketch here, I've got a 0. So remember, this is the graph of f prime at x. And I've got an x at -1. Does this quadratic open up or down? Opens up. The 6 is positive, right? The 6 in front, that's like the a value. Okay, so I've got something like this. So remember, where my first derivative is positive, that's where my original function f at x is increasing. So where is the first derivative positive? Well, it's positive here, right? And it's also positive here. That's where f prime at x is greater than 0, right? And that's where my function f at x is increasing. Okay, so I can actually see my interval from -infinity all the way to -1, and also from 4 all the way to +infinity. Those are the parts of f prime at x that are positive, or where f at x is increasing. Okay, and then, oops. Okay, where my second derivative is negative, or where my first derivative is negative, or below the axis, that tells me that my f at x is decreasing there. So I can actually see from the graph that between -1 and 4, my graph of my derivative is negative, telling me that f at x is decreasing. Okay, so this is, if you can sketch your function easily, you don't necessarily have to do the chart. If you feel good about doing the chart, then you can do it. Sometimes your function might be a little bit too complex, or you might not want to take the time to fully simplify that or graph it all out or whatever, and then you can use the sign chart. Okay, but both of these methods are acceptable methods for deciding. Olivia?
Then how do we know that -1 is a local max and 4 is a local min?
So
See that on the chart.
on the chart, we can see if the function, so you can actually even see, like from this chart right here, that this is creating a mountain, right? This first section. Okay, so on the graph, we're looking for the change between positive to negative or negative to positive, right? So because this is going from a positive section to a negative section, I have to just kind of imagine like what that's going to look like, right? So if it's going from positive to negative, I have positive slope to negative slope, right? So it's a little bit tougher to see whether those are local max or min. But yeah, in general, look for positive to negative for local min, and then negative to positive for, or sorry, for local max, and then negative to positive for local min. Good? Okay. All right, so I think this will help kind of ground that idea that you were just asking about. So it's important to know that for these types of questions, you may have different answers, okay? There should be individual things that are the same in all of these graphs, but when I'm looking at the graph of the second derivative, it doesn't tell me everything about the original function. So this guy, because it's constant, I do know that the original function was probably a linear function, right? So f at x, here's what we know. We know that it was linear because the derivative of a linear function gives us constant. Remember, every time we take the derivative, the degree goes down. So if I know what the derivative is and I do a degree up from that, that must be the degree of the original function. Okay? I also know that the slope is -2 everywhere. How do I know that the slope is -2 everywhere? Mark? Yeah, it's just going straight across y equals -2. So I must have had in the original function -2x, and then maybe I had some kind of y-intercept. We don't know. But I do know that the slope of the line is -2. So you can draw any linear function with a slope of -2, and that would be an acceptable f at x for this, okay? So for instance, if you choose this maybe as your y value, we don't know for sure that that is the y-intercept. We just want to go down 2 over 2, down 2 over 2, and that could be a graph that has resulted in this derivative. Not the greatest line, but you get the picture. Okay, so this would be our graph of f at x. Okay, so if I have a linear function for my derivative, what was the original function? Go a degree up, quadratic. Okay, so I know f at x is quadratic. Okay, we've got a 0 at 2. So where my derivative is 0, what does that tell me about the original function? There's a turning point at the value 2. The x-coordinate. Okay, we actually don't know about the y-coordinate from the graph of the second derivative. Yeah, but we do know about the x-coordinate. And then I also know one other thing. My second derivative is in the positive section here, and it's in the negative section down here. So I should know something about how my quadratic is changing. Is it going from decreasing to increasing or increasing to decreasing? Right. Okay, so one possible graph, again, we don't know where that y-coordinate is, but a possible graph might be something like this for my, maybe I'll just do this in another color, for my initial function. Maybe the turning point is there, and it must go from increasing to decreasing, so increasing to decreasing. Okay? Again, I don't know exactly where the shift of this function is, so we could all have maybe different functions and it still be correct. But in general, it should be a parabola facing down, and the turning point or the vertex of that quadratic should be at the x value 2. That's all we know. Good? Okay. Degree of the original function? 3. So it's a cubic. What else do I know? Does this function have any turning points or any areas where the derivative is equal to 0? Are you sure? Yeah. The derivative is 0 at 1. So we have a critical number, we know that, at x equals 1. So where the slope of the tangent equals 0. However, this graph is actually positive. It's in the positive section of the this graph everywhere. So what does that tell me about my original function? Mark? Yeah, so it's always increasing. So what I need to just make sure of is that I draw my graph so that it's increasing. So as I go left to right, it is always going up. But I want at x equals 1, again, I don't know how high or low that goes, but maybe my x equals 1 is like here. I want my derivative to be equal to 0 there. So maybe my function looks something like this. Okay, because my derivative, my slope of my tangent will be 0 here. Sarah?
Because it's going from positive to positive, it can be a turning point.
Right. Exactly. Mark?
So, like, is it possible to have a cubic function without turning points?
Yes. This one doesn't have any. You know that, right? For an odd degree polynomial, it could have 0 turning points. Even degree polynomials always have to have 1 turning point because they're U-shaped. Zainab?
So technically, linear functions can never have a critical number?
Yes, true. Linear functions will never have a turning point. Okay, last one. What do we know about f at x?
It has 2 critical numbers.
No.
That's a lot.
Mark? Actually, that's true, Anil. Sorry. Okay, so it goes from negative to positive to negative down here. I also have 2 x-intercepts, which are my critical numbers. So sorry, Anil. So I just shut you down way too early there. Okay, and it's a cubic, right? So it's cubic. It has critical numbers at x equals 1 and x equals 3. Now, are those maxes or mins, local maxes or local mins? So I'm going from negative to positive, which tells me this, right? So at x equals 1, we should have a local min, because we're changing from negative to positive. And then if I'm changing from positive to negative, that's telling me I have something with positive slopes to negative slopes. So that should tell me I've got a local max, right? So x equals 3, I should have a local max. Okay, I also know where this function is decreasing and increasing, right, Mark?
Like reset, like sketch.
Yeah, I'm going to, for sure. Okay, so I want my function, maybe I'll stick this here, because I want a decreasing section of my function where the area of the derivative is negative. So I'm maybe decreasing up to here. This is a local min, so from there I'm going up. I'm increasing, because that's a positive section of my graph, so maybe we go like up to here, let's say. Again, I don't know exactly where these points are. I'm just kind of making sure I draw something that fits for this, and then I'm decreasing from there, right? Because I'm in the negative section of the graph. That wasn't the best second part of that graph, but. Okay, so potentially that could be what my graph looks like. Mark?
Would it matter then, like, if you went for the second, like, local, for the max, like the local max?
Yep.
Would it matter if you went, like, above the x-axis?
Nope. Yep. Again, this graph could maybe be stretched. It could be shifted. I don't really know. The important thing is that this first section is decreasing, and then this second section is increasing, and then this section is decreasing, and that I have these numbers lining up, right? So I want to make sure those x coordinates are intact there. Zainab?
So is the second derivative, like the area or wherever like the graph is determines on like if it's increasing or not?
Yes.
Which one's second one?
Sorry, ask your question one more time just so I can make sure that I know what you're asking.
For D, how the like from 1 to 3, it's like
Okay, ladies, can you just whisper? Yeah.
above the x-axis,
Yes.
and that was like positive.
Yep. So then I had an increasing section of my graph here.
Yeah, so like would that only work if it's like the second derivative?
This is we're not talking second derivatives at all. So it's always, we're going to get the graph of the derivative, just the first derivative.
I mean like the picture there, like it's like above, so it's positive.
Yes.
Like that would only matter when it's like you wouldn't like the positive like part of the graph wouldn't matter if it's like the one that we just drew right here.
So we're drawing the original function, you know that, right?
Yeah, yeah.
Okay. So yeah, the positive and negative sections of the graph don't matter there. It's just whether the graph is decreasing, increasing, and then I want to accurately put the turning points if I have them in line with the x's.
So only for like the second.
Right. Okay, we don't know information about positive, negative for the original function from the graph of the derivative. Okay. Good? Okay. Application. So we have the temperature of a person with a certain strain of the flu approximated by the function t at d. D is between 0 and 6, and t represents the person's temperature in Celsius, whereas d is the number of days. So because d is between 0 and 6, we're talking about initial observation to the 6th day. During what interval will the person's temperature be increasing? Okay, so I can figure out where this function is increasing. I could sketch it. That's an option. I can also figure out easily where it's increasing if I find out where the first derivative is positive, right? So we're going to just use derivatives to help us with this. So I'm just going to start by taking the derivative. It will be important for me to identify the critical numbers here so that I know kind of where I'm changing, potentially from increasing to decreasing. So I'll have 5 over 18 times 2d plus 15 over 9. And then I can actually just reduce here. So I'm going to get negative 5 over 9d plus 15 over 9. And I'm setting that equal to 0 so that I can solve for my critical number. Why did I say critical number and not numbers? Mark? Yeah. There's only going to be one solution to this when I solve, right? If you want to do a really quick thing to help yourself, which why would you not? Go through and multiply everything by 9. Okay? That way I have these canceling and I can just solve this. That's much easier to solve, right? Make my life easier, not harder, right? So D equals, I think we should be able to just imagine what would go in here to make this 0. D equals, yes. Okay, or you can isolate and solve, that's fine. This is my critical value. Okay, so we're just going to do a quick little chart. I only have one critical value that I want to test here. Nope. Okay, I'm going to choose some test values. So 0 and 5, let's say. And then just kind of sub them in here and see what I would get. So when I sub in 0, I'm getting, yep, Lewis? It's between 0 and 6, right? I still want to know where that function is increasing and decreasing. Yeah, I guess we can do that, yeah. You're right. True, 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 true. Yes. We do have a specific range of values, so we'll do this. Thank you. Good. Okay, so you guys are going to sub into your original derivative here and see what we get, negative versus positive, for each of these test values, so 1 and 5. So what do we get when we sub in 1 to the derivative? Positive? You sure? Okay. And then when we sub in 5, we get negative, yeah. Okay, so when is the temperature of the person increasing? From day 0 to 3, right? So increasing over the interval 0 to 3. So between the initial observation and day 3 is what we would say. Yeah, into the derivative, yeah. Okay, not at day 0 and at day 3 because those are kind of like critical numbers, right? So it's actually evening out right here, changing from increasing to decreasing. So we wouldn't include those in our set. All right, last one. Mark. Yeah. Into the factored form? You should be able to plug it into the factored form or your original form and get the same answer. It doesn't really matter. Yeah. Okay, last one, should not take us very long. Okay, so we are going to sketch continuous functions, so no gaps is what continuous means. Guys, focus in here for the last few minutes. This shouldn't take long. Okay, so here's what I want. Sorry, the f primes are kind of like, they look like they're almost attached to the x. But we want f prime at x to be positive when x is less than 0, so on this side of the graph. And I want f prime to be negative, where x is on this side of the graph. And I want f at 0 to equal 4. Okay, f at 0 equals 4. That we can plot pretty easily, right? When x is 0, y is 4. So we want the y-intercept to be 4. Okay, now what is the rest of this asking me to do? What do I know when f prime at x is greater than 0? What do I know about f at x? Good. Okay, so I want f at x to be increasing when x is less than 0. So when x is on the negative side of the graph. So what that could look like is maybe this, right? Increasing on the left side of the graph where x is negative. And then this means when the derivative is less than 0, it means f at x is decreasing, right? So, and that's for where x is greater than 0, so on this side of the graph. So maybe something like this. Okay, and y-intercept must be at 0, 4. Does that make sense? I don't necessarily know that this is a curve. Actually, I could have even drawn like a straight line and another straight line. That could work too. Okay, so we might get different answers. Okay, so second part, I want my derivative to be positive when x is less than -1. So maybe we even just draw a little line here just to kind of show the sections of the graph. We can erase it after. And then when x is greater than 2, I also want the function to have a positive derivative or for it to be increasing. And then between those values, I want the derivative to be negative. Or in other words, I want the function to be decreasing. Yep. So in these two sections, less than 1, so from here over and greater than 2, the first derivative is positive. So I want f at x to be increasing. This guy is decreasing. So between those two values here, I want the function to be decreasing. And I also want f at 0 to be 0. So I have an intercept right there. Okay, so what's happening at -1 and 2? We're actually changing from increasing to decreasing and then decreasing to increasing. So what do I have at those values? Turning points, yeah. So I just need to place the turning points so that I can make sure that my function is doing what I need it to be doing, right? So increasing. So I want it to be increasing. Maybe I'll increase to here. And then between these sections, I want to definitely pass through 0. Then I want it to be decreasing. And then I want it to be increasing. Okay, so this is increasing, decreasing, and then increasing. Mila. I don't know. The only one that I know for sure is the 0, 0 point. Okay, so this could be like stretched much more. And again, I don't even know that it's necessarily a curve, right? It might be line, line, line. But usually we work with curves, so.
Is that okay? Like if that would have a turning point then?
Yeah, it still changes from increasing to yeah, true. Maybe like, yeah, we'll work with curves. Yeah, true, because that's more like a cusp. So yeah, don't use lines. Good point. Mark?
Those lines are not asymptotes, right?
No, yeah, we can erase those now. I just wanted to show you guys the sections as we were working. So not asymptotes. Okay. Sometimes it's just nice to like separate the sections though, so you know what has to go between them. Good? Okay. So obviously we're not going to do the questions for the test. So we'll use the last 10 minutes to do some work on this. It's just one sheet, front and back. So here's the deal. If you want to do the questions, Is everyone available at lunch? At some point at lunch, though? They're not going to take that long, are they? Okay, we'll maybe do them tomorrow then, in class.